Hello everybody and welcome to our walkthrough for the LabFlow experiment entitled Chemistry, Glassware and Measurement. I wanted to focus in on this so that you could see what this looks like and kind of get a sense of what's going on. So again, to access this, you'll be logging into the system, going to Chemistry, Glassware and Measurement, which may look like a collapsed folder here. If you're in card view, it will look like this. I am skipping over the one that's listed as chemistry, math, and labware videos. As you can see on my end, some of these are hidden from you because they're redundant with what's below. But I did leave visible the chemistry math review, which might be useful to look at this point. And also there's a video up here on using significant figures. So those may be useful for you as you're going through the week 2 material. But there's nothing sort of required in this chemistry, math, and labware folder. What we're doing is chemistry, glassware, and measurement. I'm going to switch back to the list view because I prefer it. As you go into this, you will see the similar format used for every LabFlow assignment. And that is the first thing that you'll see in each folder, each module, is a PDF file. This is important for you to read, and it's listed first because it should be the first thing that you're doing. I'm going to pop this over to a new tab. What this thing is essentially your lab manual. So this is purpose. In this case, learning how to identify and select appropriate equipment to make measurements of length, temperature, volume, and mass. Learning objectives and laboratory skills that you'll be using. Equipment and things that you would be using if you were physically in the lab, or in this case, as you're walking through the virtual lab online. Then there's an introduction. There's always going to be some background reading here, and this is important for you to read first because this will complement what's in your assigned reading for the week in the course. And this will focus more in on the laboratory techniques. So here we're talking about measurement in the lab. Measuring things like temperature with a thermometer. And shown in this inset is an analog thermometer that has little lines on it, and you'd be reading the level of modern thermometers use a type of alcohol inside there. Measuring volume. Again, this is an analog volume measuring device, a graduated cylinder, where you can put the liquid in, line your eyeball up at the same level as that liquid, and read the bottom of the meniscus. As you go on here, you'll see that there are several other types of glassware measurement, some that are graduated in that they have lots of lines on them, and you can measure different volumes using that device. Some of them, listed here as B and E, are what are called volumetric devices. Volumetric devices have only one purpose. So if you look closely at this volumetric pipette, it has a 100 on it, and this volumetric flask has a 25 on it. Those are the volumes that that particular item can measure. And that's all it can measure, but it does it very, very well. So if you were in an analytical lab where precision was of the utmost importance, you would use something like this, a volumetric device. These are also highly, highly accurate. I can't measure anything else except that one stated volume, but the piece of equipment does that very, very, very well. So most labs will have a combination of these pieces of equipment. Sort of the graduated devices for all-purpose, sort of variable needs, and then a set of volumetric glassware for making highly accurate, highly precise measurements. This also introduces for us the concept of density, which is the relationship of mass to volume for a given material. People sometimes inappropriately talk about things being heavy in terms of something like, wow, lead is really heavy. Well, sure it is, but what they're really talking about is density. So the amount of material you have, it feels heavy. It seems heavier than it ought to be. And that's a measure of how tightly packed the actual material is. In the case of lead, the atoms are packed together tightly. So we get a lot of mass crammed into a small volume. We're going to be using density as an example of an output that you might calculate from measurements in this lab. So you can read through this and read about the different types of equipment, the different types of measurements. You've got your formulas there for density as well as for percent error. The percent error formula we're going to be using a lot. It would be worth sort of noting this somewhere so that you have it later on. Percent error is always your experimentally determined value. In this lab, that'll be densities. And we subtract the accepted value. So of course we have to know that. We have to know what the density should be in this case, and that'll be given to you. Just the top part of this fraction, experimental value minus accepted value, would tell you your absolute error, how far off your number is from where it should have been. But that's kind of meaningless unless we know what scale we're on. If I tell you that my value was 10 units off, you don't know if that's good or bad because you don't know what it was supposed to be. If the number was supposed to be 20 and I was 10 units off, that's a pretty significant error. Whereas if the real value was supposed to be, say, 1,000,000 and I was 10 units off, that's not such a big error. So when we do percent error, we always take that raw error on the top, the difference between experimental and accepted value, and we normalize it by dividing by the accepted value. And that'll give us a decimal. Typically, this would be expressed as a positive or a negative to tell you whether your value is too high or too low. In this lab, they're asking you to do absolute value here, so it'll just be a positive number, okay? And then we multiply it by 100 to put it on a percent scale. So instead of getting some small decimal, you're going to get a number. I was 2% off of my target value, or 5% or 10%, whatever it might be. Just below here in the PDF is a procedure. These are the steps that you would have done if you were in the lab physically. And these are also the steps that LabFlow will walk you through. And then after that, you'll see some data collection tables. Some of these you'll be able to fill out on your own. In some cases, like this one, you need the actual data, which will be provided in the report. So I'm going to pop back to LabFlow for just a moment, and I'm going to go back to the folder. I would have read through the PDF instructions first. Then there are a series of videos here. A short video about how to use a balance appropriately, short video about how to clean and maintain your glassware, one about common glassware, and one about volumetric glassware, and then a short video about how to do basic statistics in Excel, because this lab has a small graphing part to it. Then there's your pre-lab quiz. The pre-lab quiz has to be at least completed once before you can open the report. So the pre-lab quiz and all the quizzes in this course, you'll have 2 attempts to do those quizzes. Your higher score counts in both cases, in all cases. So you can do the lab quiz once after you've read through all of this stuff. Do it once. If you're not happy with your score, you can do it again anytime before that close date. But I want to show you the report. And so I need to click into that report for just a moment. And so when I click into the report, I'm going to see here that the experiment can be completed in person or online. Obviously, we're doing this online, so you'll select virtual out of this menu and hit next. And then it's going to show you an actual data collection scheme. And so what you will do here is go through. It's showing you the couple steps in the procedure excerpted from that PDF. I've got my empty graduated cylinder sitting on this balance. This is a digital instrument, so I will read whatever it says. And now some of you will say it seems a little bit silly to just type in the number, right? The number's right there. Why do I have to type it over here? It's because we're learning how to read these devices. And with any digital reading, you're going to write down all of the numbers that you see. So whether that's a digital balance, it's a digital thermometer, digital pressure gauge, whatever it might be, if you see numbers written like this on a display, you're going to use all of them. And that's important for the significance of that measurement. This balance is reliable out to 3 decimal places on the gram scale. So I'm going to record 3 decimal places just like it says. Typically what happens is that as the balance gets to have a higher capacity, is able to measure larger things, typically that precision goes down a bit. And so, maybe if I was measuring 500 grams or 1,000 grams, maybe I would only be able to do it to a 2 decimal point precision. But the device itself would adjust the readout. So anytime you see a digital device like this, you're going to record all of the value that it gives you. Okay. Then in the procedure, I would have put some liquid in here. Now I have a new value. And so eventually, later on, I'm going to subtract those 2 to find out what the liquid actually, what the mass of the liquid was. When we see an analog scale, like this graduated cylinder with the liquid in it, They're homed in here on the value, right? So this is a 10 milliliter graduated cylinder. What I want to note here is that each one of these tick marks must represent a tenth of a milliliter, right? I've got 9 here and 10 up here, and there are 10 little spaces in between. Whenever I'm reading an analog scale like this, I want to read the number that I can see, essentially what the smallest marking is that I can actually observe, and then I'm going to estimate one more digit. And so if I look at this, I can see that that very bottom of the meniscus, to my eye, and maybe if I zoom in a bit here, we can even see it better. To my eye, that looks like it's a little bit below the 10. So if I were reading this, I would say, okay, it's definitely 9.9, and then I need to estimate a little bit more. So maybe I would say 9.98 or 9.99, something like that. I want to add one more digit. And so since this device is marked in tenths of a milliliter, my answer will be recorded to hundredths of a milliliter. Even if you think that last digit ought to be a 0, it should be recorded out to that value, okay, 2 decimal places, because I have a 1 decimal place scale on this device. That's a tricky thing to get used to. The nice thing with LabFlow is that it doesn't matter if this number is a little bit different between you and somebody else, or even what I think it should be, because this number that you type in here will be what you will use later in your calculations. So if some of you thought that was a 9.99, or some of you thought it was a 10.00, it doesn't matter. The number that you put here will be used later for your calculation. All right, the next step is to do a second trial. So here's my graduated cylinder with the liquid in it again. And again, I'm going to read this thing. Maybe I think that one's a little lower, but still 2 decimal point precision because it's a 1 decimal point scale. All right, trial number 3. Again, record all of those digits. All right, even though they're zeros, record those. And then here, I think that one's a little bit closer, so I'm going to say 999. All right, trial 4. I know this makes for a gripping demonstration. Here's one that's a little bit lower, right? So 9.9, I don't know, estimate that last digit. Maybe it's a 991. Okay. Your values for this would likely be different to mine. I'm just going through this in my little student account here. Now here's one that I think probably is actually at the 10, which is it's actually not the best way to use this device. You should never go above the topmost marking on your device because you don't have another mark to compare to. So I'm just going to say 1000. Again, 2 decimal point precision there. Now we're on to a beaker here. As you will see in the video and in the reading, beakers are not for analytical measurements of any kind. They're not designed to be accurate. They're designed to be just an estimation, just to hold liquid. All right, here we go now. This is a burette. Now we have to be careful. Burettes have the volume markings drawn backwards. So 0 is at the top, and they're typically 50 milliliter devices, so the 50 would be at the bottom. So in this case, notice I've got 2 and then 3 and then 4 down below. So when I count this, I'm going to be saying 3.1, 2, 3, 4, 3.5, and it's a little bit bigger than that, I think. So I'm going to say 3.51. Again, that second decimal place is an estimation. I've drained out a little bit of the liquid now. The final volume in the burette is down to 8.0 little something, maybe 802, 801, something like that. Okay, and you're going to go through this. I'm going to stop talking quite so much about each one and just do these. So you want to make sure that you get your values in here because they're going to be used for your calculations later. So take your time and go through these. Obviously, in my little demo, it doesn't tremendously matter if I'm super accurate, but I'm trying to do a nice job for you. 11.6, yeah, maybe 5. Okay, keep going. Trying to get through all of this. 15.85. Unfortunately, in LabFlow, I can't skip this and do my demonstration. So bear with me as I go through this. Actually, I'm going to pause the video and I will check back in just a moment. All right, we've skipped ahead just a little bit. I finished my values. Click the last one here and it says I've reached the end of the data entry section. I can review my entries or proceed to the next section. A word to the wise. If I hit review and I have to go back and change something, it gets a little bit clunky. So I would suggest that you review each one of these as you put them in just to make sure you didn't mistype something. At this point, you can go back and just double check that you didn't put in anything obscenely wrong, but then you can go ahead and click proceed. And once we've done the proceed step, now it will show me the same things with my values over here on the side. And it will have put those into the data tables, similar to what you would have seen in the PDF file, right? So this is data table 1, which looks like this. My masses and volumes are in this table. Now, the mass of the liquid is going to be a calculation. I'm going to be subtracting the filled graduated cylinder mass from the, subtracting the empty graduated cylinder mass from the filled one to get this mass of the liquid. So that's a calculation that comes at the bottom. This is just showing me all of my data, right, in tabular format. Now here's my calculations. What's the mass of the liquid? Well, look, here I have the mass of the cylinder with the liquid in it, 26.127. And just below that, I have the mass of the cylinder by itself. And so I'm just going to subtract 26.127 minus 14.465, 11.662. Okay, I'll do that for each one of these going across. Now, what's density? Well, if we look back at our PDF, it told us that density was mass divided by volume. I also can look at the units here, and I can see that density has units of grams divided by milliliters. While here, 11.662 is the grams of the liquid, the mass in grams. 9.98 is the volume I measured for that trial. So I'm going to divide these. Grams divided by milliliters. So 11.662 divided by 9.98. And I'm going to get this value. Now, how many decimal points should I keep? This is where that significant figures stuff comes in. And you will have read all of that. You've got that significant figures guide sitting next to you. The rule says that when we do division and multiplication, that we keep the appropriate number of significant figures based on the least significant value we started with. So here, 9.98 has only 3 significant figures compared to the 5 significant figures in the mass reading. So I'm going to limit my answer to 3 significant figures. So this long number you see on my calculator will round to 3 significant figures, 1.17. Okay, 1.17. And we'll do the same thing for each one of these going across. Then I've got average density. I'm just going to add all 5 of these densities up and divide by 5. And again, I'll have 3 significant figures for that. Same kind of thing is true here. I dispensed a certain amount of liquid out of the burette, so I'll subtract these numbers to get the amount of liquid I dispensed. I weighed the beaker before and after, so I can subtract these two to get the mass of the water that was dispensed, grams. And then density is grams divided by milliliters. So I'll take my calculation here, divided by my calculation there, and I'll get a number down here. Okay, again, an average. And then percent error. It tells me the density of my unknown liquid is. So what's the theoretical density of my unknown liquid? Well, they just told me, 1.190. Okay, to try to reconcile this, imagine that this bold statement is something that I wrote on the board at the front of the room, and this is the part where you wrote it down in your notebook. All right, it's not really meant to be redundant. It's just you recording that data. And then percent error. I can't do this because I didn't do all the calculations above, but remember, percent error is your experimental value. So it's saying density using the graduated cylinder. I'm going to go up to this Average density, that's my experimental value for the graduated cylinder. I'm going to subtract from that my theoretical or actual density here and divide by that same 1.190. Right, the formula is in the PDF. Oops, sorry, scrolled past it right here. Experimental value is the average you calculated in the lab, and the accepted value in both places is that number that they gave you, times 100 to make it a percent. Okay, so you'll do that up here for the graduated cylinder, and you'll do that down here for the burette. Now, it says use the table of water density at different temperatures. So how do we use this thing? I'm going to open this up in a new tab. This table probably looks a little bit unfamiliar. This is pretty typical from an engineering or chemistry handbook. The way that this works, it's the density of water with a whole lot of precision, okay? Lots of decimal places in these numbers. What you're going to do is read your temperature, because the density of any liquid changes just a vanishingly small amount with temperature. In my lab, I recorded that my thermometer reading was 21.9 degrees Celsius. Yours may be different. It's whatever you recorded up at the top of the data collection there. So 21.9. What I'm going to do is look here, go down to the 21 degree row, and then go across to the 0.9 column, and this is the value that I'm going to record. Okay, so 21.9 degrees in the room. I'm going to record that value, 0.9977957. 0.9977957. I think that's what it was. Okay, that's the number I'm going to use for theoretical density, and this, with the burette, this is the number I'm going to use for my experimental density. I'm going to calculate percent error. So if your temperature was different to mine, you would go to the appropriate degree column, or sorry, degree row here, and then the appropriate decimal point, and you'd record whatever the value is here that's given to you. Then at the bottom, there are a couple of questions, in this case, just the one sort of question about percent error, and then the upload section. Now, LabFlow is a little bit weird about its uploading things, so it'll ask you for different documents. Here it asks for a page of one sample calculation, including units. So along the way, as you're doing those calculations up above, hopefully you wrote something down. And that something could be your density calculations, it could be your percent error calculations. Whatever it is that you wrote down, you should either scan that if you have a scanner at home, snap a photo of that, just using your smartphone or your webcam or whatever it might be that you have available to you. In some way or another, you want to image that thing and then put it in here. Similarly, they say upload your report sheet and or your notebook pages. If you have something else to write down, that's fine. But in this particular case, I would consider these two to be pretty similar. So basically, if you upload something to one of these two spots, you'll get credit for both of them. All right. In some LabFlow reports, it will ask you to upload maybe a spreadsheet to one place and an image of your work to another place. Those would be two separate things, and I'm expecting to see both. But in this case, consider these redundant. So just upload your work so that I can see that you did it, okay? If you're not sure how to scan things or, if there's an equipment concern or technology concern or whatever, just shoot me an email and I can help you out. But, using pretty much any mobile device or even a webcam on a laptop or something, you can do that. So let me know if there's any problem with that, but otherwise, that's the story, okay? You can exit this report at any time until you hit the submit button at the bottom. You can go back into it and finish up later. Once you click submit, that's it. If you accidentally click submit, just let me know and I can unsubmit it for you so you can go back in and work on it. But otherwise, it'll close here on the 24th. That's the due date. I will go in the next couple of days after that and grade the manually graded parts that I have to grade, and then the grade will be represented in LabFlow. The grades from LabFlow do not automatically port back into Canvas, and so you will have to see your grades temporarily in the LabFlow gradebook but then I will bring those grades over into Canvas. I typically do that during exam weeks, and I update Canvas, kind of in batches. So you can see your grades formulating in LabFlow, and then you'll see them updated into Canvas later on. All right. So with that, things to stress here. For every lab, you will see a PDF at the top, and it is critical that you open that and look at it. You don't have to print it. You may if you want to, but you don't have to print it. But it's critical that you open this and read it so that you know what's going on. They explain a lot of critical things about the experiment, including equations and diagrams of the setup and explanation of what's going on. There will be videos here as we get further down in the course. Some of them may be repeat videos that are just kind of reminders, but you'll see they're all relatively short. They're all closed captioned and they have transcripts and everything else. So, if you want to look at the video, that's great. If you want to read through the transcript, you can do that. However you want to do that is fine. But all of the information you need for the quizzes and for the reports are contained in here. And that's it. So if at any point you want to work ahead in LabFlow, all of these other ones are available to you. They all have their due dates in the future, but they're all available to you if you wanted to go ahead and start working ahead, on your schedule. All right. So with that, I'm going to say sayonara for now. If you have any questions, please email me. Otherwise, good luck, and I will talk to you later. Bye now.